In this chapter, we're going to look at typical tasks in the context of power functions. In example 1, we're given a function equation y equals a times x to the power of 5, and we know that its graph passes through the point 2 minus 8. The task is to find a, this parameter a in the function equation. Since the point 2 minus 8 lies on the graph, we know that it fulfills the equation, which means we can insert for the y coordinate of the point, minus 8, and then for the x coordinate, the 2, in the equation y equals a times x to the power of 5. We get this equation here. So this is minus 8 equals a times 32, and dividing by 32, we get a equals minus 1/4. Example 2 is a little bit a generalization of the example 1. Now the function equation we're given is y equals a times x to the power of n, which means the exponent is unknown now, and now we're given 2 points that lie on the graph. Try to solve the task on your own, or at least set up the 2 equations, and here comes the solution. Since the point 3, 2 divided by 81 lies on the graph, we can insert the y coordinate, 2 divided by 81 as y coordinate, the 3 as the x coordinate in the equation of the function here, and we get this equation. The same we can do with the second point here, and we get this second equation. Well, this is a system of equations. The a and the n have to fulfill both of the equations, so we get here an equation system, and the first one is 1 and the equation 1, second one equation 2. Now, how can we solve that? The simplest way will be to use the substitution method. So let us solve the first equation for a. We multiply both sides by 1 divided by 3 to the power of n. So this goes to the left side, and we get on the right hand side only a. We switch sides, so we get a equals 2 divided by 81 times 1 divided by 3 to the power of n. 81 is 3 to the power of 4, and we can rewrite the whole thing as 2 divided by 3 to the power of 4 plus n. Now let us insert this result for a here in number 2, and we get 32 equals, for a, this expression here times the minus 1/2 to the power of n. Let us rewrite the minus 1/2 to the power of n as 1 divided by minus 2 to the power of n. And now let us get all the to the power of n's on the left hand side by multiplying with 3 to the power of n and with minus 2 to the power of n, and then let's get the 32 on the other side by dividing by 32. So what we get is on the left hand side 3 to the power of n times minus 2 to the power of n, and on the right hand side the 3 to the power of 4 here remains, and 2 divided by the 32 remains 1 divided by 16. Now doing another transformation, we find we're using that 16 is 2 to the power of 4. We can write here 3 to the power of 4 times 2 to the power of 4, so 3 times 2 to the power of 4, so we have 6 to the power of 4. And on the left hand side, this is just 3 times minus 2 to the power of n, so minus 6 to the power of n. And now we can rewrite the right hand side as 6 to the power of minus 4. So we have this equation, minus 6 to the power of n equals 6 to the power of minus 4, which yields that n is minus 4. We have to have the same exponent here. And since the n is now even, the minus disappears, minus something to the power of an even number, the minus disappears. So we found n equals minus 4, and the last step is to insert this n now here in 1 star to find finally a. insert here for the n minus 4, so we get 2 for the a, 2 divided by 3 to the power of 4 minus 4, 2 divided by 3 to the power of 0, 3 to the power of 0 is 1, so we get in the end 2. In example 3, we want to find where two graphs meet. This graph and this graph. Try to do that on your own. And here comes the solution. To find where they meet, we have to set the two equations equal. So the 3 minus 2 squared equals to the x to the power of 4. We see here what we have is a biquadratic equation, the x squared and the x to the power of 4. So what makes sense is to replace the x squared by z. So we get a quadratic equation now in z. To solve a quadratic equation, we need to get everything on one side. So we add 2z, subtract 3, put everything on the left-hand side to get z squared plus 2z minus 3. And this is a quadratic equation. The simplest way to solve it is using factorization. If we don't remember, we can also use the quadratic formula. Let's do quadratic factorization. We need two brackets, z plus and z minus, and the product has to be 3. And so we get z plus 3 times z minus 1 equals 0, y plus 3 and minus 1. That way we get plus 2z, what we need here. Now this yields that the first solution for z, the z1 is 1. So what we have to do now is to substitute back. So replace the z1 here by x squared. We get x squared equals 1. And to solve that, we have to take the root. So we get x12 equals plus or minus 1. For the second solution of our quadratic equation here, z plus 3, we get z equals minus 3. z2 equals minus 3. We substitute back for the z the x squared here. We get x squared equals minus 3. Well, there is no solution to that, and squared number cannot be negative. So the only solution that we have got is x1 and 2 being plus and minus 1. If x1 is 1, then we have now to find also the y-coordinate of that point. So y1, we find it by inserting in one of the two equations. Probably the simpler one is here h, so inserting it in h of 1 is 1 to the power of 4 is 1. So we get the first point of intersection, or where they meet is 1, 1. Then the second x was minus 1. To find y2, we insert that again into h, so h of minus 1, and we get minus 1 to the power of 4 is again 1. So our second intersection point or meeting point is minus 1, 1, and that's our final solution now. In example 4, we want to find all axis-intercepts of the given function y equals 1/2 x to the power of 4 minus 18. So this means the y-intercept and all possible x-intercepts. You can try to solve that on your own, and here comes the solution. Let us start with the y-intercept. The y-intercept means that the x-coordinate is 0. So we have x equals 0, and we can now insert x equals 0 directly into this equation here, and we get directly the z in that way. So the y, I want to say, which is minus 18, and we find that the y-intercept is the point 0, minus 18. To find the x-intercepts, well, for the x-intercepts we know the y-coordinate, so where the graph cuts the x-axis, there the y, or meets the x-axis, there the y-coordinate is 0, so we can insert now into the equation, function equation, the y-coordinate 0. So we get this equation here. We have to solve that, so we add 18 and multiply by 2, we get x to the power of 4 equals 36, and we take the 4th root on both sides, which means actually we take the root of the root. So the root of 36 is 6, and then again the root we get plus minus the root of 6. And so we found the x-intercepts minus or plus square root of 60 and minus square root of 60. In example 5, we also want to find the axis-intercepts of this given function, which is more complicated than the previous one. Actually, when we look at it, we see it is not even a power function, it's an exponential function, because the x is not in the base, but it appears in the exponent. To solve the task, you need just to know how to solve some of these exponential equations, as we have seen them, a little bit difficult ones. We have seen them, the type, so you can practice that, try it on your own, and here comes the solution. So, to find the y-intercept, we know the x is 0, we insert x equals 0 into the equation, function equation here, and we find that y is minus 63, so the y-intercept is 0, minus 63. To find the x-intercepts, we know the y is 0, so we set the y equal to 0 in the function equation, and we get this equation here. Now we have to do some transformations to transform the 9 to the power of x in the end to 3 to the power of x squared. Now we have 3 to the power of x squared and then 3 to the power of x here, so we do a substitution. We substitute the 3 to the power of x by a z, and we get a quadratic equation. To solve the quadratic equation, we use a factorization. In this case, we see we get z minus 9 times z plus 7. And solving this, we get first for z plus 7, the solution here is z1 equals minus 7. We have to substitute back the 3 to the power of x. We get 3 to the power of x equals minus 7. Well, 3 to the power of x cannot be negative, so this has no solution here. Then z minus 9 yields z1, the z2 is 9. We substitute back again the z equals 3 to the power of x, so 3 to the power of x equals 9. In other words, 3 to the power of x equals 3 to the power of 2, and we get x equals 2. And hence we found the x-intercept to 0.